Our first speaker is William Bonvillian. He is a lecturer in MIT's Science, Technology, and Society and Political Science departments. He is also Senior Director of Special Projects at MIT's Office of Digital Learning, and prior to this, he directed MIT's Washington, D.C. office. Bill.
Thanks, Jeff. So I'm going to talk this morning about the kind of new applied innovation challenges that are facing engineering at NSF. What's to come here? So a large part of today is going to really be about the accomplishments, but I'm going to talk about what's in store for us next. And as usual, things start with Vannevar Bush, who was President Roosevelt's science advisor. Bush, as this distinguished audience knows, authored Science, the Endless Frontier in 1945 at FDR's request. It proposed science as the next frontier for the U.S. So the U.S. had, made most of its West states by the turn of the 20th century, and it had officially closed the frontier in 1900. So Bush is proposing to pick up on the idea of frontier, which is a key to kind of American culture, and make science the next frontier. It's an exciting and interesting idea. And his report really defines the future direction of U.S. science projects and progress. He has what we now call a pipeline theory of innovation, that science with government backing is going to contribute basic research, not applied, that industry will do the applied side, apply it to practical problems. The governmental role is to increase scientific capital by supporting academic research. So he's removing science from the fray. In his words, this form of research is removed from pressure for immediate tangible results. He's protecting science in a way. He's putting it back after leading the World War II scientific effort that was highly connected. He's putting it back into his ivory tower. He calls for a new agency to carry out the directions that he proposes. He wants science in one big tent, the National Science Foundation. And it is to support this basic science, this research direction. He wants control to remain in the academy, with government providing the funding with limited supervision. That doesn't work. So this Congress passes essentially Bush's design in 1947, but Harry Truman vetoes the National Science Foundation Act that year. Bush had envisioned scientists running as the science agency. Truman asserted presidential appointment power quite properly under the Constitution. He vetoes the act. As a result, NSF's stand-up is delayed until 1950. And as a result, other agencies pop up, fill the void. That means that the U.S. has had decentralized science organization ever since that veto. Now, the critique of the pipeline model comes from a number of people, but particularly Donald Stokes, who was dean of the Woodrow Wilson School at Princeton. And his book, which this audience is very familiar with, Pasteur's Quadrant. Bush's basic research canon, according to Stokes, has two parts. It is performed without thought of practical ends. That is, and he argued this to persuade the country that attempts to constrain the creativity of basic science would be self-defeating. And his second canon, Bush's second canon, is that basic research is the pacemaker of technological improvement. And he included this to persuade the policy community that investment in basic science is going to yield technology advance and solve a broad spectrum of national needs. Stokes argues that neither of these two basic points is true. Stokes notes that the ties between science and technology are not linear. They are interactive and dynamic, that what he calls use-inspired science yields both basic and applied results. So this challenge to Bush's ideology grew insistent as the 1970s and 80s moved along, and the US shifted from a focus on science and technology from a military to more of an economic sphere, and competition grew, particularly with Japan and to some extent with Germany in manufacturing. Stokes notes, as I said, that the ties between science and technology aren't linear, they're interactive. Bush's belief was that understanding and use were conflicting goals. Stokes argues that they need to be connected. So Bush's segmented linear pipeline model is critiqued by Stokes. Stokes argues his noted Pasteur's quadrant point that there is a quadrant exemplified by Louis Pasteur's work that is use-inspired basic research. And that's a gap, a missing link in the Vannevar-Bush design. So in effect, Bush's model institutionalizes the valley of death between research and later stage development, right? So we've got basic research on one side of the valley, as this group knows, applied research innovation on the other side, the valley of death in between, and very few bridging mechanisms across that gap. So we institutionalize the valley of death in our system. Arguably, that's a significant problem. What's happened since that debate? So we've moved towards models that reach further down the pipeline, that make more connections between the R&D and the implementation side. And of course, the best example is the Defense Department. The United States is running essentially two parallel R&D systems on the non-defense side and the defense side. On the non-defense side, organizations like NSF, Department of Energy's Office of Science, NIH, follow a basic research model in the Bush design. They undertake research, maybe some early stage development. At the Defense Department, it can't work with a disconnected model. It undertakes and funds and supports the research, the development, the prototyping, the demonstration, the test beds, the initial production and initial market creation in many cases. So it stretches down the entire pipeline. So we're running these two parallel systems in the US. What about the non-defense side? We've had, I would argue, roughly 5 periods where the US has tried to kind of better connect science and technology, all driven by historic crisis-oriented kind of events. Period 1, as we've just discussed, is the immediate post-war period when we move from a World War II connected model to a more disconnected model under Bush's design. Period 2 is where the Department of Defense really reconnects. DARPA comes about in this period. This is the space race. NASA is a connected organization. Period 3, that's the 1980s competitiveness period, the challenge from Japan and to some extent Germany. The US has to develop a series of models to better make the connection between R&D and the kind of back end of the innovation system. Programs like the Manufacturing Extension Program, the Small Business Innovation and Research Program, the Bayh-Dole Act, the Advanced Technology Program, the R&D tax credit for industry. All of these came out of that 1980s competitiveness period to get better in implementation. A fourth period could be the energy challenge in the 2000s. The ARPA-E model came out of this period, but also greatly expanded institutional elements at the Department of Energy. Energy Frontier Research Centers, Energy Innovation Hubs, the Advanced Manufacturing Office at DOE, the Technology Transfer Office, the Cyclotron Road Model, the DOE Loan Program. All of these stretched further down the pipeline from DOE's Office of Science and its focus on basic research. Period number 5, maybe we're in this around advanced manufacturing. We've created 16 manufacturing institutes that are public-private, industry, university, government collaborations. These are to really be test beds around advanced manufacturing technologies and their implementation. So it's not just those changes. NSF, of course, has changed, given that Stokes-Bush debate, to make better connections itself. So many changes within NSF to make it a more connected institution. NSF's engineering directorate, as Jeff just mentioned, created in 1981. The SBIR program for small business innovation came out of NSF. Engineering Research Centers in 1985 that will be discussed tomorrow. Major NSF initiatives in areas like advanced manufacturing, the National Nanotechnology Initiative that NSF really originated and spread to other agencies as well. Focus in manufacturing around cyber-physical systems, around biomanufacturing and other areas. In education, the IUSE program in cooperation with NSF's EHR for undergraduate STEM education, the I-Corps in 2012, its broader impacts and grand challenges approaches that bring us closer to use-inspired research. And then more recently, NSF's 10 big ideas, 10 big initiative areas for societal results. So all of those move parts of NSF down the pipeline within a still basic research model. But now we're starting to see, really in the last few years, emerging industrial innovation policy approaches. So the US has long had industrial economic policy elements in agriculture, in energy, things like hydropower and nuclear, fossil and renewable subsidies, power regulation, in ag, price controls, the irrigation systems, land grant colleges, the extension agents, then in health, in Medicare and Medicaid. These are all economic interventions, but the US government has played a limited role outside defense in industrial innovation policy arenas. What is this? Industrial innovation policy really means a focus on the post-R&D stages of technology implementation, late stage development, prototyping, testing, demonstration, the production prototype, production itself, initial market creation. The US has generally stayed out of this in the non-defense arena. Economists have opposed it as governmental interference in markets, but there are three new drivers. As Dan referenced and John referenced earlier, technology competition with China, climate change and the new energy technologies required, and lately the pandemic. All of these have been driving a more connected system. And that geopolitical driver is particularly significant. So we've had a series of major new industrial policy initiatives in the last few years. I think most important of all, most comprehensive, was Operation Warp Speed, a massive intervention into vaccine development with guaranteed production contracts to industry, a portfolio approach where government picked key vaccine technologies it would support, a technology certification program, integration of federal officials into companies to speed development, governmental controlled distribution systems, dramatic interventionist activity at later stages in the pipeline through that law. The CHIPS Act just passed, $52 billion in appropriations for new fabs and foundries for semiconductors, as well as advanced R&D in semiconductor areas. The infrastructure bill passed in 2021 had major energy technology demonstration centers to be set up. $20 billion worth of these for carbon capture and sequestration, hydrogen, advanced nuclear, critical minerals, renewables, and a new technology demonstration office to be set up at DOE. A White House effort on securing domestic supply chains in 4 critical technology areas. And then most recently, the Inflation Reduction Act, $375 billion for new energy climate challenges. These are tax and consumer incentives largely for implementation of efficient technology. So major interventions further down the pipeline in the last few years. And then particularly for NSF, the science part of the CHIPS and Science Act that just passed, known previously as the Endless Frontier Act, the Innovation and Competition Act, the Competes Act, and now more recently, the CHIPS and Science Act, major new role for NSF. This is an authorization, not an appropriation yet, but nonetheless, it creates a whole series of new avenues for NSF in particular. And it came out of a concern that technologies innovated here in the United States were not scaling up here. They were being produced there. And the goal here was to get a range of critical new technologies into industry acceptance here, with the technology competition with China as a major motivator. It creates a new technology directorate at NSF. NSF is obviously our one major broadly focused R&D agency, not tied to a specific narrow mission area. It's largely basic research with evolving exceptions, as I've noted. But with NSF is to be a new technology-focused subunit, TIP, now created. Many argued that this would create a culture clash within NSF, but we do have a long history of running basic and applied programs within agencies. They can complement each other, and they can get back to that Stokes critique of the need for technology innovation to influence basic science and vice versa. So you create a two-way street in science. It's an enabler in a way. Still, that new directorate is going to have to shift from NSF's basic science peer review culture. What's it going to do? What are some of the follow-on elements in this Endless Frontier Science and Chips Act? R&D in critical technology areas, and they identified 10 areas that the new technology directorate is going to have to take a lead on. The final legislation added societal goals to the list for things like underperforming regions. Some key elements got dropped. The university technology centers were dropped. The test bed demonstration function was dropped. The scale-up financing provision was dropped. NSF is undertaking regional innovation centers. At the same time, the Act authorizes EDA and NIST at the Commerce Department to create 10 regional innovation hubs. On workforce education, there's major investments in STEM education, but largely left out is a focus on the technical workforce. On manufacturing, there's limited funding for advanced manufacturing, pretty limited scale. So there's issues in this bill around tech development. Can a technology development effort be created within a basic science agency? We're going to find out. Regarding regional innovation hubs, these are high-risk efforts, right? The United States has not figured out how to create regional innovation clusters in any kind of efficient way. The performance failure rate is really quite high in these attempts. But we're now charged with trying to tackle this and create a new geography for reviving U.S. regions. On workforce education, how are we going to deal with the technically skilled workforce that's largely not included? On the manufacturing front, we're going to need to do the manufacturing job better, and that's really not much of a focus in this act. On supply chain, we really need a financing provision that's kind of missing from this law. But nonetheless, it signals, I think, that a new era of industrial innovation policy is starting up. The Defense Department has always done this, but our civilian agencies, particularly including NSF, are going to have to develop these capabilities. They're going to be charged with these kinds of capabilities. It's going to require completely new thinking by scientists and engineers. They're going to have to master new skills. It's not just research anymore. They're going to have to be change agents connecting across these systems. They're going to have to connect the research foundations with the follow-on stages. They're going to have to understand the manufacturing foundations. They're going to have to learn how to map supply chains and fill in gaps. There's testing and demonstration capabilities that are going to need to be mastered. We're going to need to integrate between agencies, industry, and universities, as well as across agencies. We're going to need to do better at technology certification and validation to speed technologies into place. We're going to need to use the flexible contracting mechanisms that we now see, the Defense Production Act, other transactions authority. And we're going to have to learn how to master those outside of the defense side. We're going to need technology scale-up financing expertise too. So there's a whole new set of tasks, very engineering-oriented. They're going to need to come to play. So industrial policy appears underway at scale. We're not really ready to implement it. We're going to need a systems of innovation approach versus Vannevar Bush's linear model, I would argue. We're going to need to look at innovation in a dynamic way. We're going to need to look at the barriers and bottlenecks to the needed information flows and innovation flows. A scattered agency approach is not going to work. We're going to need to tackle this scale-up problem and the financing behind it. And we're going to need really a whole new infrastructure for implementation that operates across agencies and uses a range of governmental assets. So big tasks ahead, and NSF is going to need to be at the center of these. Thanks very much.
Thank you, Bill, so much for that wonderful talk. We have a few minutes before the start of Thomas's talk, and so I'll pose a few questions, or at least one. Bill, you spoke a lot about the need for greater interagency cooperation, and you were the director of the MIT Washington, D.C. office for many years, so I assume you interacted with many different agencies. So I'm wondering if you could speak about the cultures of the different agencies and how they evolved, and for instance, in an area like biomedical engineering, it seems like cooperation between NIH and NSF would be essential. And how are the cultures of NIH and NSF similar or different, and how has that evolved over time?
I mean, Jeff, you're absolutely right. We've got a big issue here now upon us, and it's, as I noted, it all stems from Vannevar Bush's design. This time, he wanted 1/10 for science, a loose, kind of flexible tent, but he wanted 1/10 for science, and he didn't get it when Harry Truman vetoed his legislation. So we got a scattered approach and a whole set of mission-based agencies. Now, there's a lot of advantages in that, right? Having a mission-based justification for an agency really helps in its survival and funding and support. And it also gives lots of opportunities to scientists to fit their research into different, agencies and funding opportunities. So there's very good things about it. I think overall decentralized is probably a good thing. But as we attempt to take on what I've called this industrial innovation task, right, I think we're going to have to rethink the model. So, we set up the Office of Science and Technology Policy to do the coordination between the agencies. But OSTP is a small operation, very few permanent staff, largely borrowed from the agencies every time OSTP is stood up. It has no budget responsibility. So that fundamental budget power that's so key to federal governance, it doesn't have. It's got to rely on cooperation. So getting the agencies to collaborate here is going to be a tricky task. We've seen some good examples. NSF was at the heart of one important one, the National Nanotechnology Initiative. A central office was created, different agencies contributed. That didn't change the fact that we had a bunch of different appropriations committees moving in different directions, but nonetheless, a lot of collaboration was created in that kind of NNI model. And I think that's a promising approach to begin to tackle some of these questions. The Obama administration had a series of life science initiatives, Jeff, getting back to your point about bioengineering and medical research, around the BRAIN Initiative, which brought together DARPA, NIH, NSF, FDA in a kind of a collaborative kind of effort. These kinds of common initiatives are really needed here. We've had some success in the manufacturing initiatives. The directors of the 16 manufacturing institutes are on the phone together at least every other week, trying to figure out common strategies and success models together. We're going to have to learn how to do this much better. So I think your question is a big one and an important one.
One other area I found especially intriguing in your talk is discussion of regional clusters and attempts to build new centers and new regions and new agglomeration economies, basically. Do you see any learning during the pandemic and how we have used information technology to communicate. It probably varies greatly in terms of the types of engineering, but do you see new opportunities that from the learning that occurred during the pandemic?
Yeah, Jeff, I think, we all had to go on Zoom, right? And that was a great forcing mechanism. There was kind of nothing like it. But let me step back for a second. We need to do this spread of innovation to larger geographic areas. We can't get away with a bicoastal innovation system with a few stops in between. That's not working for our country. It's a divisive problem. So we need to solve this. And the Chips and Science Act, calls for EDA at the Commerce Department to tackle this with a series of 10 regional innovation hubs organized around the critical technologies identified in the legislation. It's going to be a big challenge. And we don't really know how to do this very well. The number of successful regional innovation clusters that have been consciously stood up, as opposed to kind of evolved based upon regional strengths, there's very few. So if we're going to tackle this geographic inequality problem, and Thomas, I know, we're going to talk to us in a minute about the larger economic inequality problem. We're going to tackle this geographically. We're going to need to learn how to do this. And NSF is moving down this pathway, even though it has no experience, frankly, in this field in any depth, right? ERCs are a possible exception. But it's moving down this pathway too, and that role has now been recognized in the legislation, in the final version of the legislation too. But it's going to be a big challenge. And at the same time, we're locked in this big geopolitical contest, frankly, with China. And we're going to have to make sure that our efforts to do geographic regional innovation don't offset our ability to continue our strong focus on overall technology leadership, huge lessons for which we just learned from the semiconductor experience and the nightmare of semiconductor supply problems that we ran into in the last year and a half. But going back to your original point, do the pandemic information tools give us new tools? You bet. The fact that we can do this conference on Zoom and have a much better audience reach, the fact that we're all used now to using these new IT tools is terrific. I do a lot of work on workforce education. Video conferencing systems are not the optimal education tool, right? You can't build in a lot of what we know about learning science into these video conferencing services. Asynchronous video, where you can build in continuous assessment, 10-minute, presentation systems to make up for mind wandering, where you can build in, a certain amount of difficulty to make it challenging for students. You can do that much better in asynchronous video. So we shouldn't mistake Zoom for the optimal education model. But in terms of connecting people and enabling idea exchange, it's great. And in fact, when NSF picked up the internet from DARPA handed the internet off from DARPA's internet to NSFnet. NSF really scaled the internet by bringing it to virtually every major university in the United States. It was the scaler of the internet. DARPA was just connecting a relatively modest number of computer science departments. NSF really scaled it because NSF saw it as a tool for research collaboration, which indeed it is. And now, as a result of the pandemic, we have new face-to-face tools as well.
Thank you, Bill. My historian colleague, Jan Abate, has done some great work on the history of NSFnet and a very important topic, and until her work, relatively unstudied.